Various definition of graph and some definitions. Okay, we have discussed about what is the graph. Discuss about what is the graph, what is the null graph. Okay, what is the finite and infinite graph. Okay, and what is the handshake theorem. Handshake theorem. What is the handshake theorem? And definition of walk, path, and circuit. In last lecture, we discussed about graph, null graph, finite and infinite graph, and handshake theorem, and walk, path, and circuit. Today, we will discuss some example on walk, path, and circuit. And already we have discussed about the definition of walk, path, and circuit. Okay, already we have discussed about the walk, path, and circuit. Now we consider the example of walk, closed walk, path, and circuit. In this example, the example is given in this example. Here a graph is given, and we have to find out the open walk, closed walk, and path and circuit in this given. So what is the open walk? Open walk means we are traversing on the graph from vertex to vertex. Okay, maybe repeat edge or maybe repeat vertices. Okay, so now we are traversing here from V2 to V4. V2 to V4 we traverse. So this is the V2, E7, V5, E8, V1, E8, V5, E6, V4, E5, V4, E5, and V4. So we traverse from V2 to V4 from using any pair of vertices here. Now closed walk. We know by the definition of closed walk where initial vertex and final vertex are same. If we moving on the graph in such a way that their initial vertex and final vertex are same, then it will be a closed walk. So in this example, we are moving from V4 to V4 is an example of closed walk because initial vertex and final vertex are same. Path. In path is also a walk in which vertex are not repeated. Vertex are not repeated, but in walk, vertex may or may be repeated here. So in this path, the path is V2 to V3, V2, E7, V5, E6, V4, E3, and V3 is a path. Just to see here, no vertex are repeating here. Circuit. A circuit is a closed walk in which initial vertex and final vertex are same. And here example is V4, V2, E7, V5, E6, V4, E3, V3, E2, V7 is a circuit. In this case, the initial vertex and the final vertex V2 are same or no vertex is repeating here. This is the circuit. Some observation about the walk, path, and circuit. In walk, vertex or edges may be repeated. This is a open walk. In closed walk, walk in which initial and ending vertex are same. In path, it is a walk without repeated vertices. In circuit, it is a closed walk in which vertices are distinct, no repetition of vertex except initial and ending vertex. The number of edges in a walk is called a length of a walk. In previous example, just we see the previous example, the length of the open walk is the number of edges is E7, E8, E8, then E6, E5, and E5. The total, the length of vertex is 3 because E8 is repeating here, so we are neglecting them. The total length of walk is 3. So this is the example of open walk, closed walk, and circuit. Now connected and disconnected graph. A graph is said to be connected if there exists at least one path between every pair of vertices. Otherwise, graph is said to be disconnected. A null graph of more than one vertex is a disconnected graph here. And a disconnected graph consists of two or more connected graph. Each of these components are known as the each of these connected subgraph is known as the components. So what is the components? Components is in a disconnected graph. The various connected subgraph is known as the components. In example, there are two subcomponents First is, this is the example of, this is the connected graph. This is the example of connected graph. Okay, because of between every pair of vertices, there is a path exists. If suppose we have to move from B to D, so there is a path. If you move to from B to H, there is a path. So between every pair of vertices, there is a path. So it is a connected graph. If we remove B to F here, if we remove D to F, then the graph will become disconnected here. So simple example. The example is, suppose we have the 4 vertices here. Suppose this is the vertices, and one edge is connecting with this graph here. So, okay, so this is your A, B, C and D. This is F. This is the F, E, E, F, and this is G and H. Okay. Now this is the connected graph. If we remove the edge DF, then it will become a disconnected graph. If we remove this graph here, now this is the disconnected graph, and these are 2 components. So these are 2 components here, which is the any subgraph of various subgraph of disconnected is known as the components. So this is the component 1 and this is the component 2. So we get here 2 components. In similar, the another example is here. This is the graph. This is also graph, but they are not connecting. Here, this is not connecting. So this is the disconnected graph. Okay, and there are G1 and G2 are the 2 components of this disconnected graph. Okay, so now discuss about walk, path, circuit, and connected and disconnected graph, which is depends upon the definition of path. Now, very, very important concept in a graph theory is isomorphism of graph. Now we discuss what is the isomorphism. Iso means isomorphism. Iso means same, and morphism means image. Morphism, image. That means 2 graph, they have the structurally they are different, but their internally structure are same. The graph is known as the isomorphism graph, means same image. So we discuss about what is the isomorphism. Isomorphism is very general concept appear in the several area of mathematics. We already discussed about in algebra. We have discussed about in group theory about the isomorphism. In graph, what is the definition of isomorphism? We discuss here. The word derived from the Greek iso meaning equal or same, and the morphism meaning to form or shape. Okay. So isomorphic graph, 2 graphs are isomorphic if they are structurally identical, which means they have corresponds structural details. This is the very important point. When we are finding the isomorphism of graph, then we have to find what is the corresponding structural details of edges and vertices. 2 graphs G1 and G2 are said to be isomorphic to each other if there is 1-to-1 correspondence between their vertices and their edges, such that the incidence relationship preserved. Okay, incidence relationship preserved means there should be for the graph G1 and G2, if you have to check out whether both are the isomorphic or not, then we have to find the corresponding vertices of both G1 and G2, and their vertex and edges should follow the incidence and adjacent relationship. Okay, we discussed what is the meaning of incidence relation preserved. Another definition: 2 graphs G1 and G2 are said to be isomorphic if there exists 1-to-1 correspondence between their vertices and edges, such that F is G1 to G2, such that F is G1 to G2 only if their images, suppose there is E1 comma E2 are images in G1, then such that F of E1 comma F of E2 belongs to G2. This is the condition of 1-to-1 correspondence. Okay, such that E1 comma E2 belongs to G2, then F of E1 comma F of E2 belongs to G2. Okay, note that if G1 and G2 are isomorphic, then it is denoted by G1 is isomorphic to G2. Then G1 is isomorphic to G2. In figure it is given, suppose this is the structure of G1 and this is the S2. This is E1, E2 are the two edges in G1. Then there are two one-to-one corresponding. The image is f of E1 and this is the f of E2. Okay. So now we discuss the example of isomorphic graph. What is the basic condition for being isomorphic? The number of edges must be same. That means in graph G1, E of G1 equals to E of G2. That means number of edges in G1 is equals to number of edges in G2. The number of vertices must be same. That is V of G1 equals to V of G2. That means the number of vertices in G1 is equals to the number of vertices in G2. And their edge connectivity must be retained. And the number of vertices are same degree must be same in G1 G2. Means कि the number of vertices जितने भी vertices G1 में अगर डिग्री सेम है उसकी G2 के साथ में भी सेम होना चाहिए. Thus two graphs are said to be isomorphic if they have the same number of vertices, the same number of edges and equal number of vertices with a given degree. The above conditions are necessary but not sufficient for a graph. It is not necessary कि if these four conditions satisfy, then the graph must be a isomorphic. The graphs, both graphs must be isomorphic. This is condition necessary but not sufficient. We will explain this example after this first example. We will explain this one. This is the consider this example. The two graphs are given here, and we have to check out. Yeah, we have to test ki whether both graphs are isomorphic or not. The graphs are V1, V2, V3, V4 and this is the V5. Okay, so these are the two graphs are given here. This is the G1 and this is the G2. And we have to test whether both graphs are isomorphic or not. Okay, so in definition we have discussed about the incidence relationship preserved. That means we have to find the corresponding vertices of G1 and G2. Okay, what are the corresponding vertices of G1? Okay, now for finding the corresponding vertices of G1 and G2, first we have to check the basic condition. Okay, what is the basic condition? Yeah, necessary condition for a graph be isomorphic. The condition is number of edges in graph G1. The number of edges in graph G1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Is 6. And now number of vertices in graph G2. Number of vertices is 5. So number of edges is 6 and number of vertices are 5. In graph G2, number of edges in graph G2. Number of edges 1, 2, 3, 4, 5 and 6 and number of vertices in graph G2. So there are also 5 conditions. So this is the initial condition, yeah, necessary condition कि in both graphs should have the equal number of edges and equal number of vertices. So which is satisfied by the graph G1 and G2. Okay. Now graph G1 and G2. Now we have to find the corresponding vertices. Okay. Now we define. Now this condition is satisfied. Then now we define the another condition here. कि for isomorphism, if such that G1 to G2, if such G1 to G2, define a mapping. We define a mapping here. Define a mapping f G1 G2 such that, okay, such that, okay, so here just to see f of x1 है ना, f of x1, the image of f of x1, where the x1 is corresponds to, we have to find the corresponding vertices of x1 and of g1 and g2. Here x1 is a vertex, okay, which having the degree 3. Okay, now we have to search a similar vertex in graph g2 which have degree 3. Here either v1 or v2 both are the having the 3 degree. So we take here v1. Here we take x1. Okay, why we take? We can't take x1 is not corresponding to here v2 because the degree of v2 is 2 and x1 is degree of 3. So both cannot be a corresponding vertices. So f of x1 equals to v1. Here we find, that means this can be written as ki x1 is corresponds to v1. Ki in graph g1 x1 is a vertex and their corresponding vertex we are taking in g2 as v1. Okay, now f of x2 equals to, we are taking v of 2, that means x2 is corresponds to corresponding to v2. Similarly we are taking f of x3 equals to, okay, f of x3 equals to v3, that is x3 is corresponds to v3, and f of x4 is having the image in v4, okay, v4, and here is the x4, and that is x4 is corresponds to v4, and f of x5 is equals to v5, that is x5 is correspond to v5. And this is a very important concept, ki how we find the corresponding vertices in graph g1 and g2. Here the degree of x5 is 1, so that x5 is a pendant vertex, and then similarly we have to find in g2 ki which one is the pendant vertex. So here v5 is the pendant vertex, so x5 is corresponds to v5, that is f of x5 equal to v5. Okay, similarly here x4 is corresponds to v4, that is f of x4 equals to v4. Why? Because the degree of x4 is 3, here is also degree of v4 is 3, and x4 is adjacent to a vertex, pendant vertex x5. Here is also ki v4 is having the degree 3 and which is adjacent to a pendant vertex v5. So both are the similar, both are having the same characteristics. So they preserve the incidence relationship, okay, in adjacency and in also incidency. Okay, so these are the corresponding vertices we have find out, and these all satisfy the conditions. They are having the corresponding vertices. So this gives the corresponding vertices of g1 and g2. So these are the correspondence vertices of g1 and g2. These are the corresponding vertices of g1 and g2. Okay, we have already found out this one. Okay, if there is no any corresponding vertices between in g1 and g2, then we say the graph is not isomorphism. This is a non-isomorphism. Okay, clearly the mapping f is 1 1 and on 2. This is f1 is 1 1 on 2. Okay, and thus the g1 and g2 is the isomorphic to each other. So we have no any, we have all the vertices having their corresponding vertices. So it is a 1 to 1 mapping. This follows the definition of 1 to 1 mapping. Okay, so the corresponding vertices, after finding the corresponding vertices, we see the graph g1 is isomorphic to g2. Both are structurally different, but their relationship, the incidence relationship are same. So the graph g1 and g2 are both are the isomorphic graph. Okay, so we say in last we say ki f such that g1 to g2 is isomorphic. Okay, now we take the second example here. Here these all necessary conditions are defined here. All the necessary conditions are satisfying, but the graph is not isomorphic. how we see why the graph is not isomorphic here. Consider the graph. We consider the graph here. Here okay, so this is V1, V2, V3, V4, and that is V5, and it is V6. The another graph is okay. So this is A1, A2, A3, A4, A5, A6. This is the graph G1 and this is the graph G2. Now first we have to find the basic condition here. Number of vertices in graph G1 and number of vertices in graph G2 both are same, and number of edges in graph G1 and number of edges in graph G2 both are same. So how many vertices in G1? Suppose for G1 we find the vertex set is here V1, V2, V3, V4, V5 and V6. Okay, and number of edges, so number of vertex equals to 6, number of edges 1, 2, 3, 4, 5. Number of edges is 5 here. And for G2 we find vertex set. This is V1, this is V2. Sorry, this is the V, and this is the this is the U here. So this is A1, A2, A3, A4, A5 and A6. Okay, so number of vertices equal to 6 and number of edges equals to 5. 1, 2, 3, 4, 5. So this follow the basic condition here. Okay. Now we have to find the corresponding vertices of G1 and G2. So how we find the corresponding vertices of G1? Okay, we have to find the corresponding vertices of G1 and G2. Just to see here, only the vertex V4 having the degree 3 here in this graph, and in this graph the vertex A3 has the degree 3 here. So we see that V4 is corresponding to A3 or not. This is the question mark here. Now we have to check where V4 is corresponds to A3 or not. That is f of V4 to A3 or not. If there is no any corresponding vertices, if one of the vertex not having the corresponding vertex in G2, then we say it is not a isomorphic graph here. Now see here, this is the structure here. See here, the V4 having the degree 3 and A3 is also having the degree 3. Okay. Next, V5 is a pendant vertex which is adjacent to V4. Here is A4 is a pendant vertex which is adjacent to a A3. Okay, but the another adjacent vertex of V4 is V6, which is a pendant vertex, but A3 having the two adjacent vertices A2 and A5, and both have the degree 2. So there is no any pendant vertex. Okay, that means V4 having a adjacent vertex is V6, which is a pendant vertex that is degree 1, but in this graph A3 have two pendant vertex A2 and A5, and both have the degree 2. So there is no incidence relationship between V4 and A3. Okay, so graph is not isomorphic. The graph is non-isomorphic graph here. So we prove there is no any corresponding vertex of V4 to in graph G2. So this is the non-isomorphic graph. So this is not corresponding vertices, no fx. Now we see here V1 is degree 1. So V1 is corresponds to A1 might be possible, this okay, this okay. Then V2 is corresponds to A2. Yes, V2 having the degree 2 here. Okay, here A2 is degree 2 here, but the corresponding vertices, the adjacent vertices A3 of A2 having a pendant vertex, but here the V2 having the adjacent vertex V3, which is have the degree 2, and no pendant vertex, adjacent pendant vertex with this V3. So the V2 is not isomorphic to A2. So similarly, we can take many example here, and the graph is non-isomorphic. If that means we have no corresponding vertices in V4, in G1 and G2, so the graph is non-isomorphic graph. Some theoretical part I am just reading. In graph J, we observe that the vertex V4 is only vertex of degree 3, while in graph B, the vertex of degree 3 in A3. In order the graph A and B are isomorphic, that the vertex V4 in A must corresponds to the vertex A3 in B, since there are no other vertices of degree 3. In graph A, the pendant vertices adjacent to V4 and V5 and V6, while in graph B, the pendant vertices adjacent to A3 is only one, namely which is A4. Hence, V4 is not corresponds to A3, and thus the given graphs are non-isomorphic. So there is a simple approach to find out the isomorphism of graph, just to find the corresponding vertices and find the incidence relationship. They are not satisfied, then we say the graph is non-isomorphic. This is the example of isomorphic graph and non-isomorphic graph, and definition of isomorphism. Now we discuss the another definition. What is the Euler graph? This is a Euler graph. The definition of Euler graph depends upon the definition of walk, path and circuit we already discussed previously here. A Euler graph may be defined as any connected graph is called an Euler graph if and only if all its vertices are of the even degree. This definition have some theoretically, if we prove this one, practically we can easily prove if any graph having the all vertices are even degree, then the graph is Euler graph. But we take the another definition for the conceptual part. An Euler graph is a connected graph that contains an Euler circuit. This is a very, very different key. We say a graph is Euler graph if it contains Euler circuit. Now what is the concept of Euler circuit? Now we discuss on the Euler circuit. If there exists a circuit in the connected graph that contains all the edges of the graph, then the circuit is called an Euler circuit. That means we have to find, suppose a graph is connected graph, and we are traversing on the graph in such a way that it contains all edges. It contains all the edges of given graph, then the circuit is called an Euler circuit. We know what is the circuit. Circuit is in which initial vertex and final vertex is same, but no vertex is repeated here. But Euler graph, you to visited all the edges and return to the initial vertex. Okay. If there exists a walk in the connected graph that start and ends at the same vertex and visit every edge of the graph exactly once, that means without repeating any edge more than once, with or without repeating the vertices, then the such walk is called a Euler circuit. Okay. That means we have to move in a graph, we have to visit all the edges, but not repeating without repeating the vertices. But initially we have to return again. We have to return at the initial point. Okay. So this is the graph is the Euler graph. This is the example here. Here is a connected graph, and all vertices are even degree. Therefore, it is a Euler graph. This is the practically it is. This definition is okay. The graph is connected graph, and it having all the vertices of even degree, then the graph is Euler graph. But conceptually when we go, so when we have to find the Euler circuit, what is the Euler circuit here? So this is the example of graph. So there are 3 examples here. Just to consider an example here. Okay, so this is A, B, C, and this is D and E. Okay, so we consider here 2 definitions here. First, if any graph having all even degree, then the graph is Euler graph. The another definition is if any graph having the Euler circuit, then the graph is known as the Euler graph here. So first see, so all vertices having the even degree. Okay, here degree of A is 2, है ना? Similarly, degree of B is 2, है ना? So all other vertices for C, for D, for E, and for, है ना, for D. So all having the even degree, so the graph is Euler graph. Now we consider second definition. Now we have to move on a graph, and we have to visit all the edges of the graph and returning to the initial point. Then it is known as the Euler circuit, and the graph contain Euler circuit is known as the Euler graph. Now what is the Euler circuit in this graph here? Now you have to find the Euler circuit. Euler circuit. Now suppose we start from the B. So we have to visit all the edges. B, A, C, B, A, C, E, D, D, then C, and then B. Means first we move from B to A, then A to C, C to E, and E to D, and E to D, and D to C, and again coming to the initial point here, B. So this is the Euler circuit, hence the graph is Euler graph. Graph is Euler graph. Okay, suppose how we check the graph is Euler graph? Just to see if all the vertices having the even degree, then the graph is the Euler graph. There is no any need to check whether the Euler circuit are not there. Okay, simple. This is the observation is given. If any graph is the even degree vertices, then the graph is known as the Euler graph. The another definition, if we are moving in a graph by covering all the edges exactly once and returning to the initial vertex, such walk is called Euler line, and a graph consists Euler line is called a Euler graph. Similar to previous definition. Now there are some observation about the Euler graph. What are the observation? A graph which contains an Euler circuit if and only if all vertices are even degree. So here this is the Euler circuit. Just to see what is the degree of B? 2, degree of A is 2, degree of C is 2, degree of E is 2, degree of D is 2, degree of C is 2, degree of B is 2. So this is the Euler graph. Okay, Euler circuit. The Euler line contains all the edges of the graph, then the Euler graph should be a connected graph. Okay. For non-connected graph we can find for the disconnected graph we can find the Euler graph. It can't be because there is no exist path between two vertices, so it is not possible. The Euler graph does not contain isolated vertex and pendant vertex. This is a very important concept. Okay, suppose this is the isolated vertex V1. So we can't move from one edge to one vertex to another because there is a single vertex. So this cannot be a Euler graph. Now we consider example of pendant vertex. Here V1 and V2 are both having the pendant vertex here. The degree of V1 is 1, degree of V2 is 1. Okay, so this cannot be a Euler graph. Why? Because if we start from V1, we goes to V2, but the returning point, we can't repeat the edge here. So we can't return this initial point, so this is not a Euler graph. That means any graph having the pendant vertex cannot be Euler graph, or any graph having the isolated vertex cannot be a Euler graph. And all the vertices of an Euler graph should be a even degree. So these are the some observation about the Euler graph. Now that is a very important part is Hamiltonian circuit. Okay, now we discuss about the Hamiltonian circuit. Hamiltonian circuit. Now what is the basic difference between Euler graph and Hamiltonian graph? If we see here, Euler graph focus on visiting on edges, but Hamiltonian graph focus on visiting vertices. This is the basic difference between Hamiltonian graph and Hamiltonian and Euler graph here. Okay. A Hamiltonian graph may be defined as if there exists a closed walk in the connected graph that visit every vertex of the graph exactly once except starting vertex without repeating the edge, then the subgraph is called a Hamiltonian graph. That means in Hamiltonian graph we have to visited all the vertices here. We have to visited all the vertices and returning to the initial vertex but not repeating any edge. Then such type of closed walk is known as the Hamiltonian graph here. Another definition, any connected graph G that contains a Hamiltonian circuit is called an Hamiltonian graph. Now what is discussed, what is the Hamiltonian circuit? Okay, Hamiltonian circuit is a connected graph, is a closed walk that consists each vertex in a graph G exactly once except starting vertex at which the walk to be terminate. That means we to visited all the vertices of the graph and again return to the initial vertex. Then the graph is known as the Hamiltonian circuit, and the graph having the Hamiltonian circuit is known as the Hamiltonian graph. Here we discuss one definition here. The given graph is a Hamiltonian circuit having Hamiltonian circuit. If having the Hamiltonian circuit, then it will be the Hamiltonian graph here. So consider the graph okay, so this is the A, this is B, C, D and E and F. Okay, now we have to find the given graph is Hamiltonian graph or not. So first we have to check whether it is have the Hamiltonian circuit. The graph contains a closed walk. First we find the closed walk. We have to start from visited to visited. So we see then A, B, C, D, E, F and A. This is the Hamiltonian circuit. Hamiltonian circuit. Okay, A, B, C, D, E, F, A having the Hamiltonian circuit. Okay, so the given graph is Hamiltonian graph. It visit every vertex of the graph exactly once except its starting vertex, because we have to return again A. So this is the closed walk. The edges are not repeated during the walk, therefore it is a Hamiltonian graph, or having Hamiltonian circuit, so it is a Hamiltonian graph. This is a simple example. We have to visit on all the vertices without repeating any edges. Okay, if we find out this, then it is a Hamiltonian graph. So what is the basic difference between Euler graph? Euler graph focus on visiting on edges, but Hamiltonian graph focus on visiting vertices. Now some observation about Hamiltonian circuit here. In Hamiltonian circuit, degree of each vertex is 2. Just to see, this is the Hamiltonian circuit, and degree of each vertex is 2. Degree of each vertex is 2. Degree of each vertex is 2 here. A Hamiltonian circuit is a graph of n vertices consist of exactly n edges. Okay, suppose this is the Hamiltonian graph. Okay, so Hamiltonian circuit of n vertices. How many vertices here? 6 vertices, and this is also a Hamiltonian circuit. So all the number of edges in a Hamiltonian circuit is also a 6. 1, 2, 3, 4, 5, 6. So the concept is a Hamiltonian circuit in a graph n vertices consist of exactly n edges. So here, how many vertex? 6 vertex, and the number of edges in a Hamiltonian circuit is 6. So n equals to 6 and e equals to 6. We have some two examples, some more examples here. How we find the Hamiltonian graph and Hamiltonian circuit of the graph here. The suppose this is the graph. The intersecting point is also a vertex here. So we define here vertex is V1, V2, V3, V4 and V5 here. And here now this is the Hamiltonian graph. This is the any graph. This is the any graph. Now we have to find the Hamiltonian circuit. Now that means we have to visit all the vertices and return to the initial vertex. So first will be, suppose we are moving, we are going this, this, this and this. Okay, so this is the graph. So this is V1, V2, V3, V4 and V5. Okay, we are visiting all the vertices 1, 2, 3, 4, 5 vertices 1, 2, 3, 4, 5 vertices. Okay, so this contains the Hamiltonian circuit here. So Hamiltonian circuit will be, suppose this is the E1, this is E2, this is E3, this is E4, this is E5, this is E6, this is E7, this is E8. Okay, so this is E1, this is E2, this is E3 and this is E8 and this is E9. So Hamiltonian circuit is V1, E1, V2, E2, V3, E3, V4, E8, V5 and E9. Okay, just to see how many number of vertices in graph G here. So in graph G 1, 2, 3, 4, 5. So here is 1, 2, 3, 4, 5. The number of edges in Hamiltonian circuit, the number of edges 1, 2, 3, 4, 5. That means the number of vertices in graph G is 5. So the Hamiltonian circuit has 5 edges. This is the observation. Okay, what is the another? So there are so many Hamiltonian circuit exists in graph G here. The another one is, suppose we draw stuff. Okay, so this is the another Hamiltonian circuit V1, E1, V2, here is E6, that is V5, that is E7, V3, V4 and this is E3 and this is E4. Okay, so this is the another Hamiltonian circuit. Okay, and see the degree of each vertex is 2. The degree of V1 is 2, degree of V2 is 2, degree of V3 is 2, degree of V4 is 2, degree of V5 is 2 here. Similarly for this example, Hamiltonian circuit, so we have all vertices having the degree 2. So this is the Hamiltonian graph. Okay, now we have discussed about Hamiltonian graph and Euler graph. Now there are some examples of Euler graph but not Hamiltonian graph. So this example, this is given, this is the graph. Okay, this is the graph Euler graph but not Hamiltonian graph. We see that the degree of each vertex is even degree in a graph. So this is a Euler graph. By just look the graph, by the finding the degree of the each vertex, we can find the given graph is Euler graph. So in this graph, the Euler graph, all the vertices of graph having the even degree. So it is a Euler graph, but not a Hamiltonian graph. Can you say why this is not a Hamiltonian graph? Okay. Why? No, this is this example gives the both are Euler graph and Hamiltonian graph. So we have discussed. So sorry, I am again repeating here. So you have to give an example. You have to give an example of a graph which having which having Euler graph and Hamiltonian graph. Hamiltonian graph. Okay. So first you have to find the given in example. So this is the this example. This is the Euler graph as well as Hamiltonian graph here. Okay. Now second example, you have to find the second example. You have to example number 2, example of a graph which is Euler graph but not Hamiltonian graph. Hamiltonian graph. Third, you have to give an example of a graph which is Hamiltonian graph, but not Euler graph. Okay, so this is the example which is a Euler graph. Here just to see, this is the graph. The first graph is the example of which having which is Euler graph, but which is Euler graph as well as Hamiltonian graph. The second example, this is the example which is the Euler graph but not Hamiltonian graph. Just to see why this graph is not a Hamiltonian graph here. So I am taking the example number 2 here. We have completed example number 1. The example number 2, just to see a graph here. Okay, just to see the graph. One, two, three, four, 5. Okay. Suppose we have to start. We have to visit all the vertices here. So suppose I start V1, V2, V3, V4 and V5. Suppose I start from V1. So this one, I visited this one, I visited this one, I visited this one. But again I am returning. Then it is the repeated. So this is not a Hamiltonian graph. Why this is the Euler graph? Just to see degree of each vertex is even degree. V1 is 2, V2 is having 2, V3 is having 4, 2 and 2. So even degree, each degree of each vertex is even degree. So this is the Euler graph. Directly we can check out. Okay. Now this is completed. Then another example. The example of a graph which is Hamiltonian graph but not Euler graph. Okay. The example is given here. Just to see. Okay. This is the Hamiltonian graph but not Euler graph. Just to see Hamiltonian circuit, easily we can find. We to visit these and this. This is the Hamiltonian circuit. Okay, so Hamiltonian graph but not Euler graph. Why? Degree of this vertex is 3. Degree of this vertex is 3. This is 3, not even degree. So it is not a Euler graph. So this is a simple example of Euler graph. Simple example of Hamiltonian graph but not Euler graph. So we have considered here 3 examples here. Okay, just to see, practice out. Okay, thank you so much. Okay.